And there's basically three applications we're going to look at. One is what it's called the instantaneous rate of change. And I'm going to go through an example here. Let's see. Let's take a look at this. Now, let's say we have this. We've got a circle. And its area is expanding. So you can kind of think of this as like if you spill something on the ground and it's just expanding out. Now, the area in terms of the diameter and this is what we're going to get. So I'm going to establish my lower bound here. It's A equals pi over 4 d squared. The diameter d. Now, the thing we want to find out is this. How fast is the area changing? When the diameter and this is going to be a big one. It's going to be 10 meters. It's a pretty good size diameter. So the idea with this type of question is that we want to think of the area as a function of the diameter. So the area depends on your diameter. So we would say something like A of D is pi over 4 d squared. So this is going to be the area at a given diameter. That we're interested in is how fast it's changing. So if we just want the area, well, you plug it in. And this will round out to about, grab a calculator real quick. About 78.54 meters squared. Now that's just an area. But that's actually not what we're looking for in this problem. When the diameter is 10, when the area is this size, how fast is this area changing? And for us, it's going to be expanding. So to answer that question, we're going to compute dA, d diameter. And so that's going to be the derivative of that function. And what this is going to come out to is pi over 4 times 2 times d, or, we'll not go so quickly. We'll get this. And this will simplify to pi over 2d. So this is going to give us the rate of change of the area. Now, this is in terms of diameter. It's interesting because it's not in terms of time. You think of area changing over time, but in this case, we're thinking of it changing with respect to diameter. So what we'll do to find out this rate of change at 10 meters, remember this notation. Do something like this. This will be pi over 2 times 10. That comes out to about 15.71. And just double checking the units. It's meters squared per meter, which is kind of a funny thing. But the reason the text isn't going to simplify this, because you could say this is meters squared over meter. Usually when you're dealing with units, you'll cancel meters. Meters will divide into meters squared. So you get 15.71 meters. But this is kind of nice to have it like this. This tells us this is an area relating to a length. And this tells us we have a change of 15.71 area units per length unit. So it's interesting that they would leave that there, but it kind of makes sense. So any questions about that? Now, the thing to keep in mind here is that the area is changing differently at different values of diameter. So the ADD, let's take D equals 20. Will this be pi over 2 times 20? Let's see. Let me double check that there. For 2 meters squared per meter. So what you're finding is that if we're looking at the diameter growing, it's an independent variable that could change, say. We're getting that the rate of change is different for different values of the diameter. So this is a kind of an interesting property of what we would call a dynamic system. Now, the other thing we want to talk about, we've looked a little of this already, is motion. And so we're going to use something called a position function. So this is the position of something at time t. And what we typically say is that the change in position from time t to time t plus delta t, it's going to be given as this. Delta S is the position at t plus delta t minus the position at time t. Another term for this is what we call displacement, or a change in position. So that's what we're going to mean by changing through space. If you're at one position at time t, and then as time passes, you'll be in another position. The distance you've traveled, you take the distance, you take the difference between your positions at, say, different times. So, for example, if we say this is your position at time t, and that's your position t plus delta t, then the displacement is delta S, which will be S of t plus delta t minus S of t, which is 5 minus 1, or 4. So any questions about that? So when we talk about what's called an average velocity, and this came up a bit when we were talking about an object falling near the surface of the Earth. So it's a little bit of a review. But what it is, it's oftentimes written like this. Maybe not always the best notation, because of when you get into vectors, this might look like a vector. So in the text, what they use is they're using this, V av. And this is when you take the displacement, delta S, and you divide by that change in time, delta T. And so this will be S of T delta T minus S of T over delta T. And then we're going to get something called instantaneous velocities. Now what's happening here is average velocity is, you don't always capture, for example, if you're changing your velocity, speeding up, slowing down, this doesn't always capture that. So for example, let's say you have S of T. You have S T plus delta T. And let's say this is 100 miles. And let's say delta T is 2 hours. So you go from S of T, this could say be like Roswell, and then you go to S of T plus delta T, this could be like Vaughn. And the average velocity is going to be your delta S over your delta T. That's going to be 100 over 2. You'll get 50, and this is going to be miles per hour. Now, when you're driving, you're not always driving, well, unless you use the cruise control, you're not always going to be going 50 miles per hour. As you're driving from, say, Roswell to Vaughn, you could be slowing up, speeding down, if you're passing someone, if you're letting somebody pass you. Also, the speed limit, it varies. Once you get past outside of Roswell, it's going to vary from 65 to 70. And at least that's what I remember. Maybe I'm not remembering that correctly. But I think you have a slower speed just outside of Roswell and just outside of Vaughn. You have a slightly faster speed limit in between. And there's going to be different reasons why you're going to slow down. There might be an animal crossing the road, various things. Another thing is you might, someone might need help. You might pull over and help somebody and stop for a while, and then you keep on going. But the bottom line is that a lot of different driving behavior is going to be happening here. But when we calculate average velocity, it's just the distance you traveled and how long it took. So the distance divided by how long it took, that's your average velocity. So what we're going to be looking at here, our main interest is what's called instantaneous velocity. Now, this is where we get to look at how your speed is changing as you're driving from Roswell to Vaughn. So this is going to be the velocity at a particular moment in time. And so the way we define this, we call this a function v of t, or ds dt. Or the limit is delta t goes to 0 of f of t plus delta t minus f of t over delta t. Oh, and they're using f, I'm using s. So I'm going to stick to my function s. And so what this will do is this is the instantaneous velocity, or the velocity at time t. So let's do an example. Let's see here. So any questions about this? I'm going to go through an example. We'll look at average velocity, instantaneous velocity again. So let's say we have something like this. So let's say we drop. And we've seen this already, but we're going to drop an object near the surface of the Earth. And when we do this, we have our object here. This would be, say, t equals 0. And we can drop it, and it's going to say drop, let's say 3 seconds, like t equals 3. Or we'll say t sub 0. So we're going to release this thing, and it's going to fall down here. The distance it falls so the distance the ball has fallen at time t is given by, and we're going to use the metric version of this. So we saw the English units version, which is 16t squared. We're going to use the metric version of this, 4.9 t squared. So this tells us how far the ball has fallen once we've released it in terms of time t. So t0, it's up at the top, and then time ticks by and the ball falls. So let's say we have this. So let's calculate the average velocity from t equals 1 to t equals 3. So if you think about this, what we have here, we can kind of think of s of t in this case. It's going to be s of 1. Delta t is going to be 3 minus 1, or 2. And then s of t plus delta t, I'm just using the parts that we have here, but it's just going to be s of 3. that future time. So that's how all these parts go together. So we have delta t. We still need to find delta s. So delta s will be s of 3 minus s of 1, or 4.93 squared minus 4.91 squared. Run that through a calculator real quick. 44.1 minus 4.9. And so we get 39.2. And this is going to be meters. I'm sorry. Yes, we are doing metrics. So we're going to be meters per second. If we were using the 16t squared formula from the beginning of chapter 2, we'd be using feet per second. So this is the average velocity. Any questions about that?
Yes. Where did the 4.9 come from?
Oh, so the 4.9, that's part of the formula. So the formula for how far the ball has fallen is 4.9 t squared. What it really is, and I'll go into this formula a little bit more, what's going on with it, is the actual formula is 1/2 gt squared. And g, for the metric system, so if you're using meters instead of feet, g is 9.8. But if you're using feet in the English system, g will be 32. And so this will give you two different versions of this formula. For the metric, you'll have 1/2 times 9.8 to give you 4.9 t squared. And then for the English, you'll have 1/2 times 32, and that gives you 16 t squared. So,
Okay, thank you.
no problem, but that's where those are coming from. And it depends, again, what system you're using. You're usually using the metric system in a physics class, but sometimes you can use this. So that's the idea of average velocity. Now, for instantaneous velocity, now we're going to find two velocities here. We're going to look for instantaneous. Now, the average velocity was 39.2 meters per second. And that's if you calculate the average velocity from t is 1 to t is 3. Now for the instantaneous, we need to take the derivative, excuse me, of our position function. And we're going to stick with the metric one. So we'll get 4.9 times 2t, which is 9.8 t. So this is going to be ds dt. So ds dt at t equals 1 will be 9.8 times 1, or just 9.8 meters per second. And ds dt at t equals 3 will be 9.8 times 3. That'll give us 29.4 meters per second. Let me see, there's something, my average seems to be, I'm gonna double check something here. Oh, let me go back, look at my average velocity. I think I forgot to divide by 2. Yeah. So let me go back to my average velocity. I see I made a mistake. I forgot to divide by 2. So these are the two speeds for instantaneous. Let me recalculate that average velocity. I apologize. I forgot to divide by 2 in that. So in your notes, I'm just going to put the instantaneous velocity. That was, let's see, 9.8 meters per second. Let me do that average again. So in your notes where we calculated the average velocity, I forgot to divide by the delta t, the 2. So it's s of 3 minus s of 1 over delta t. And then let's see, that would be 4.9 times 3 squared minus 4.9, 1 squared. And then we need to divide by 2 our delta t. I forgot to do that. So we get 44.1 minus 4.9, and we still need to divide by 2. 44.1 minus 4.9 is not enough for the average velocity. We have to divide by 2. So then we get to 39.2, divide by 2. So you get 9.6. So for the average velocity, you should have 9.6 meters per second. I apologize. I accidentally forgot to divide by the 2. So any questions about that? Because we're going to take a look at this and see what kind of conclusions or interesting points we can draw. Now the average velocity, and again, this is from time is 1 to time is 3. That's 19.6 meters per second. Again, it's not 39.2. We needed to divide that by the delta t. There's 2 seconds between 1 second and 3 seconds. So when we divide by delta t, we get 19.6. Then let's take a look at this at the instantaneous speed at 1 and the instantaneous speed at 3. So the instantaneous speed at t equals 1 is 9.8, and it's smaller than the average. And then you look at the instantaneous speed at t equals 3, it's 29.4, which is a little bigger than the average. And when you're taking an average, that kind of makes sense. You know, you would kind of expect that the average is going to be bigger than the smaller value, but smaller than the bigger value. So in this case, that makes sense. That makes pretty good sense. Now, any questions about that? Let me give you a little more commentary. So the thing with velocity, though, you could be doing all kinds of crazy things with velocity. So for example, you could drive up from Roswell to Vaughn, and about halfway to Vaughn, you realize you forgot something really important. You're like, oh, I was going to drop this off at a friend's place and I forgot it. So you had to drive all the way back to Roswell and then go all the way back to Vaughn. And that's going to play havoc with your if you're tracking your velocity, it's going to be doing all kinds of crazy things. And we can think of it like this. Let's say you have a friend in Vaughn, you're in Roswell. And when you're going from Roswell to Vaughn, we might call this a positive displacement. But then if we go from Vaughn to Roswell, we're going backwards. So this we might call a negative displacement. So what does that do for our velocity? Well, in this case, we could get a negative velocity. So for example, let's say we have our number line. And here we are at position 1, and this would be, let's see, 2, 3, 4, 5. And we'll put a 0 over here. And let's say at S time is 1, we're at 4, but at S time is 3, we've gone backwards to 1. So if we were to calculate an average velocity, we get delta S over delta T, or S3 minus S1. Then we have 3 minus 1. And then we're going to get 1 for S3, 4 for S1. We get 2 for delta T. We'll get minus 3 halves. So you can have negative velocity. And what it does, it tells you really which direction you're going. So it's going to indicate a direction of travel. So what we're going to do is, let's say we're not interested in direction of travel. We just want to know how fast you're going. And so that is going to be speed. In this case, there's no sign with speed. We just want to know how fast you're going. We're not interested if you're traveling from Roswell to Vaughan or backwards from Vaughan to Roswell. We just want to know your speed. So when you talk about driving like in a car, when you look at your speedometer, it's always telling your speed. It's not telling your velocity. So speed is the absolute value of velocity, or the absolute value of the derivative of the position function. Questions about that? All right. So there's two other concepts to mention here. The other thing that's interesting in this section is what's called acceleration. If velocity is measuring the change in position over time, or the displacement over time, acceleration is the change of speed or velocity, I should say, over change in time. And so for the average acceleration, this will be the change in the velocity over the change in time. And then we're going to have instantaneous acceleration, which in this case is going to be the derivative of the velocity. Just like velocity was the derivative of position. Now, we do know, though, that velocity is the derivative of position. So that means we're taking the second derivative of the position function, or you might see it written as S double prime. So questions about that? I'll go over an example. So let's say we have this. Let's go back to our position function. S equals 1/2 GT squared. And let's go with the metric system. We'll go 4.9 T squared. So for A, let's find the average acceleration from t equals 1 to t equals 3. Now, from before, the velocity at time equals 1, which was the derivative of the position function at time equals 1, that was 9.8 meters per second. And then the velocity at time equals 3 was the derivative of the position function at time equals 3. Let's see, what was that one? Double check. 29.4. So to find the average acceleration, we're going to take the velocity it's going to be delta v over delta t, or the velocity at 3 seconds, minus the velocity at 1 second, over 3 seconds minus 1 second, or 29.4 minus 9.8 divided by 2. And let's see, what is that going to get us? Well, 9.8 meters per second squared. Now, this might seem not too significant, but this should be what we get. You see, the G value for the metric system is 9.8. And we're going to find out in a little bit why this is a significant find. But so far, we've calculated average velocity. It's 9.8 meters per second squared. Now, let's compute the instantaneous acceleration. At t equals 1 and t equals 3. So for this, again, S of t is 1/2 gt squared, or 1/2 times, we're going to go with 9.8 again. We're going to use the metric system, t squared, or 4.9 t squared. So again, keep in mind, g is going to be 9.8. So the velocity, which is the derivative of position with respect to time, well, that's going to turn out to be d dt. And we've seen this before, but we'll run through it again. This will be 9.8 t Now that's just for the velocity. Now if we calculate the acceleration, well, this will come out to be just 9.8. And as you can tell, this is going to create an interesting result. This means A of 1 is 9.8. And A of 3 is 9.8. So what we find out in this situation, whether we're computing average acceleration, the acceleration at time is 1, or the acceleration at time is 3, the acceleration is the same. Now again, let's think about what acceleration means. Acceleration tells us how the speed is changing as time passes. So that means, are you speeding up? Are you slowing down? Now what this means is that the ball, if you're thinking of a ball, again, dropping, is speeding up at a constant rate. So this is one of the facts of physics, that for near the Earth's surface, if you're falling near the Earth's surface, you're constantly speeding up at the same rate. Your speed is increasing at the same rate. So questions about that? All right. So another thing that comes up is economics. So we're going to get into something that we call marginal cost and marginal revenue. So marginal cost is this. It's your increase in cost when you produce, or to produce. Say it this way, increase in cost to produce one more. It's a term called widget. So widget's just kind of a generic term for just one more item that you're making. So when you talk about in economics, if you're producing something, if you're manufacturing something, you might be making cars, maybe you're producing shoes, whatever it is, generically we call those widgets. We have marginal revenue. And so this is the increase in revenue. To produce one more widget. So we typically, in text, we're going to represent what's called the cost function to talk about these things. And the cost function what's going to be the cost to produce X widgets. And then you're going to have a revenue function. What's the revenue earned from producing X widgets? So any questions about those before we start putting them to work? So now marginal cost and marginal revenue, we might limit those to say the additional cost to produce one more item or the additional revenue we get for producing one more item. But we might look for something a little more precise. Let's see, I'm looking for a different, I think they are still calling it marginal cost as h goes to 0, but so for revenue and cost, we might be interested in less discrete. And discrete means like adding one. In this case, we might be interested in adding like, what's the cost to make half of something, half a widget? So when this is the case, we might be interested for an instantaneous change in cost or revenue. Put it another way, not just change resulting from X increasing by 1. So this is going to bring in our derivative. And so we're going to look at a cost function. We're going to look at a revenue function. We're going to find, basically, we're going to compute the marginal cost and the, let's see, that if I'm using the quite, I don't think they give ones for revenue. Well, instantaneous change of revenue, we'll say that. Now, marginal cost is talked a lot in economics. So if you do take an economics class, this is going to come up. So they might not take it as far as calculus. So let's say we have a cost and revenue function. The cost and revenue functions to produce between the 8 and 30 radiators is. Now this might be a strange thing to say, they produce between 8 and 30 radiators. But the idea is that cost is going to change as you produce more of something. And it's not just because you're using more materials. You're also going to be using a lot more electricity. You might be using more heat. You might have people bumping into each other. You might have, with a lot of people on a factory floor, a person can run into another, and then that's going to, there might be an injury that needs to be dealt with. So cost is going to change. It's going to have a strong relationship between how much manufacturing you're really doing and not just the materials you're putting into your product. So let's say we have this. So this is our cost function, this is our revenue, and this is where X is going to be between $8 and $30. So the questions we're going to ask is this. Find the change in cost and in revenue to increase production when you are producing $11 radiators. So what that means is that if we're producing 11 and we want to increase the 12, what's that looking like it's going to be? Can we estimate that? And so the way we're going to estimate it is we're going to compute the change in cost and the change in revenue using a derivative. So the change in cost this is going to be dc dx. And so what that's going to give us is we take the derivative of x cubed. We'll get 3x squared. Derivative of negative 6x squared, this 2 is going to hop down and multiply to the 6. Minus 12x. Derivative of 15x plus 15. So the change in revenue which is dr dx. Again, derivative of x cubed is 3x squared. Derivative of negative 3x squared, this 2 will hop down, we'll get negative 6x. Derivative of 12x is 12. So what we can do and we can call this, we'll use what they use in the text, we'll call this C prime, call this R prime. So the change in cost, if we're already producing 11 radiators, we calculate that by C prime of 11. It's 311 squared minus 12 times 11 plus 15. Then we break out a calculator, we figure that one out. Oh. And so we're going to get 246. And this is going to be dollars per widget. And then for the change in revenue, this will be R prime of 11 over 3 times 11 squared minus 6 times 11 plus 12. Let's see what that's going to be. That's $309 per widget. So what this means, if we increase production from say 11 to 12, we're going to increase cost $246. We'll increase our revenue $309. So any questions about that? All right. So that's just some of the applications that you're going to be looking at in this section. I want to move into 3.5. This is going to be more sort of formulas. And just for the sake of time, I'm sort of watching the schedule. So I'm going to kind of push through this one a little fast. But these are going to be for trig functions. Now the proofs for these are in the textbook. So if you want to see why these are true, I'd recommend looking at those. We'll do one proof type or one We'll do one for tangent. But the formulas for the derivatives of trig functions are going to be this. So the derivative of sine x is cosine x. The derivative of cosine x is minus sine x. The derivative tangent x is secant squared x. The derivative of the cosecant of x is going to be the, let me double check my signs here. Negative cosecant cotangent. Derivative of secant is going to be secant x tangent x. And the derivative of cotangent is minus cosecant squared of x. So these are your derivatives of trig functions. And again, they've got proofs for these. Let's see here. They have cosine and they have sine. So let me show you just how they come up with tangent here. And so these are going to be some of the calculus formulas that you're going to want to memorize. Like you've had to memorize like the Pythagorean theorem in the past. This is going to be something for calculus. This is some of the calculus formulas you want to hang on to. But let me show you how they do tangent. Any questions about these? All right. So the derivative of the tangent of x, what we'll do is break this down into sine x over cosine x. And what we can use the quotient rule. So we'll bring this back. So d dx of f over g g f prime minus f g prime over g squared. And I'll be honest, I get that one. That's one I tend to forget. So I'm just going to double check just to make sure. Okay, just want to make sure. So what that means, we're going to let g be cosine x and f be the sine of x. So we're going to get cosine, and then we're going to take the prime of f. This is sort of a funny way of writing a derivative, but you'll see people do this sometimes. They'll put the function in parentheses and put a prime on it. That means they're going to take a derivative. They just don't want to write d dx in front. So we get sine of x, and then the derivative of cosine divided by cosine x squared. So then, derivative of sine is cosine. Yeah, cosine x, cosine x, minus, then we have sine x. Derivative of cosine is negative sine. Again, those formulas, you're just going to have to put together a little cheat sheet and just kind of practice those. Keep those with you when you do your homework. So square cosine, you get cosine squared. So this here, minus and minus, that's going to become a positive. So we're going to get cosine squared x plus sine squared x over cosine squared x. Well, cosine squared plus sine squared is 1. So you get 1 over cosine squared x. And this is just going to be secant squared x. And that's how you get your derivative of tangent. In fact, for all of these, once you know the proof for sine and cosine, and there's a neat trick they do use for that. I'll admit, if we had time, I'd like to go over that. But you can follow along fairly. I think it's fairly straightforward. They don't leave anything out in their derivation. You can see how they come up with those. And then once you have a sense of how to compute those, you believe that the derivative of sine is going to be cosine, the derivative of cosine is negative sine, then all the other trig functions you can write in terms of cosine and sine, and then use your product rule, use your quotient rule, and your other derivative rules to compute the other derivatives. So let me do an example. Let's say we have something like this. Now, there's different ways you can approach this, but let's say we're going to do the product rule. So let's say we're going to do product rule. We're going to break it up right here. So this means, I'm going to use that convenient notation. I'll take the cosine of the first function, or take the derivative of the first function, I should say, times the second function, plus the first function times the derivative of the second function. So we got to take the derivative of this plus this. So that's going to give us the derivative of sine x, because the derivative of a sum is the sum of the derivatives. So we get the derivative of cosine x times secant x plus, and then we have our sine plus cosine. And so now this is where we pull out our little cheat sheet we flip back to the book and we take a look at some of these formulas that we're just starting to learn. So the derivative of sine, well, that's going to be cosine. The derivative of cosine is negative sine. Plus derivative of secant is secant tangent. And then we can distribute. We'll get cosine x secant x minus sine x secant x plus sine secant tangent minus, we have cosine secant tangent. Now to simplify this, let's rewrite secant and tangent as sine over cosine. So that's 1 over cosine minus sine one over cosine sine over cosine this is sine x cosine x minus cosine x 1 over cosine x and then sine x over cosine x. So now we can simplify things. So we can see here, simplify a little bit. There's a cosine and a cosine, those are going to cancel. There's a cosine and a cosine, those are going to cancel. And it looks like we're going to get a sine over cosine, sine over cosine. We're going to have a 1 here, then a cosine squared and a sine squared. So 1 minus sine x over cosine x plus, looks like a sine squared over a cosine squared minus a sine x cosine x. And this will give us 1 minus tangent x This is going to be a tangent squared x. And then we have minus a tangent x again. And then 1 plus tangent squared x. Well, that's going to turn into something. Minus 2 tangent x. This will be secant squared. And so that's going to be your answer. Questions about that? So there's a number of problems here you're going to be working with that use your trig, your new trig formulas. We got about 10 minutes left, so let's see. Let's look for one here that's going to be interesting. Let's do this one. So I was hoping to get to the chain rule today. We'll have to save that for next Monday. But that one shouldn't take too much time. So let's say we have this. We want to find dp dq. Well, what we'll get, d dq, 5 plus 1 over the cotangent of q. Or, and again, the derivative of a sum be the sum of the derivatives. So the derivative of a constant is going to be 0. We're going to have this. And we're going to break it down to f and to g. So again, using that quotient rule, g f prime minus f g prime over g squared. Or cotangent q times 1 prime minus 1 times cotangent q primed. Again, that prime means we're going to take the derivative. And then we have cotangent squared of q. So the derivative of a constant, again, that's going to be 0. What's the rate of change of something? Rate of change of something constant? Well, there is no rate of change if it's constant. That's going to be 0 times cotangent q, which is going to be 0, minus 1 times, and then the derivative of cotangent, again, you look on that little chart or that cheat sheet, negative cosecant squared q. Then we have cotangent squared of q. So negative and negative will be positive. So you have a cosecant square root of q that's positive over cotangent square root of q. And we can simplify this. What we can do, let's take cosecant. Well, that's 1 over sine. So cosecant squared, that's 1 over sine squared. Cotangent squared, sine squared. Oh, no, I'm sorry, cosine squared. Over sine squared. So what we can do, we can multiply of this complex fraction. The complex numerator we can multiply by sine squared q. This large denominator we can multiply by sine squared q. And what will happen is it'll cancel with the sine squareds here. And what that's going to leave us with is 1 over cosine squared q. And then what's 1 over cosine? That's secant squared q. And that's going to be your answer. So questions about that? So pretty much the homework for 3.5, you're going to be given a bunch of these. And they're just going to kind of hammer them out, get some practice. Let's see. And that's pretty, there's going to be a few other ones there. That's some, but mostly that's what it's going to be. And then we don't have time for chain rule. We'll be looking at chain rule on Monday. So that's going to be it for today. We got about 3.5 minutes left. So you have your test due tonight if you're still working on the exam. If any questions about that, let me know. I'm going to have office hours from 4 o'clock to 6:30 this evening also. And then I'm going to check the homework schedule, make sure things looking like we're staying on schedule. But we're through 3.5 and we're going to keep charging along. So if any questions, let me know. Other than that, have a wonderful day.